Okay, welcome everyone. I would need my slides. Great. So, one question up front. Is anyone here who wants to see the talk in English? Okay, great. Okay, so my name is Gerion, and we'll talk about Satisfiability Modulo Theories. Using open source to solve hard problems. And I'll do a very gentle introduction and then show a few applications that might be interesting, I hope, to see or to give a glimpse at how it's used in practice and what hard problems might be in practice. So, okay. Okay, so let's For everyone who just thought, oh, it's about solving interesting stuff and has never heard of Satisfiability Modulo Theories or SMT before, let's start with a few quick things where it's already used. So if you are using OpenSUSE and installing any packages on there, then you're the thing that computes which packages depend which ones and which one you need to install additionally is powered by a SAT solver, which is also the base for an SMT solver and essentially, yeah, one subcomponent of that one. And this might also motivate one thing where it's used. I'm sorry, this project doesn't have a nice logo, so you can't see a lot. But there's a pretty old project that deals with verification of C and C++ programs and checking whether it adheres to a certain specification. It's called CBMC, and it's used quite a lot in academia and certain other projects. VCC is a pretty well-known checker for C and C++ program with a specific focus on concurrent programs. It's by Microsoft Research. And if you've heard Daphne or Boogie, this is from the same tool set. So it also uses Boogie in the back end. This is just a paper, but I found it a very nice project. So if you happen to use LLVM and you happen to compile programs that use floating point numbers with LLVM, then it does all kinds of interesting optimizations on your programs to make it run faster. And there was an interesting paper where they tried to verify whether these optimizations were actually correct. And we'll see a bit later how that turned out. Then you might have heard of CLE. CLE had a pretty big splash at some points when they verified core utils. So our beloved Linux programs or Unix programs like copy, move, all this stuff. And it turns out that if you look at these programs from like the lens of formal verifications, there were quite a few bugs in there and inconsistencies and all the stuff. And now they also use SMT in the backend. And then there's a very flashy example. Amazon by now has regular talks with the title "A billion SMT queries a day." And they mean that quite literally. So if you're using Amazon AWS access policies, then they use SMT solvers a bunch to look at your access policies and make sure you are not doing stupid stuff, like opening up by accident to the whole world, or letting people in that should probably not have access to your resources. So let's start with the basics. So the title of the talk starts with satisfiability. So in its core form, satisfiability is a question: do we have that's why it didn't work. Do you have Boolean variables, so true or false, such that the logical formula is satisfied, so that it evaluates to true? And if you're not that familiar with logic in the mathematical sense, but rather programmer, that is my question. Can you assign A, B, C, D Boolean variables to values such that this condition evaluates to true in any of our regular core languages that we mostly use? And maybe surprisingly, there's a whole lot you can already do with that. So if you look carefully at that and think about what A, B, and C and D might mean and what you can do with these logical formulas, then you can ask, okay, assuming, for example, A is, should I install a certain package? And my formula is used to specify inter-package dependencies. You can ask, is there a selection of packages from my package repository such that all dependencies are satisfied? And I install a certain package, of course. Or I can ask, given I have a program and my Boolean variables are bits of program variables, is an input to the program such that I segfault, given that you can properly specify when a segfault occurs. Maybe you just want to ask, is there undefined behavior? Are there values to program variables such that an LLVM optimization is actually behavior preserving? Or also, is there an unexpected way to access an S3 bucket? And now you might think about, okay, how can we square that with these Boolean variables? And yeah, sometimes Boolean is not enough. And this is where the second part of the title, Modulo Theories, comes into play. And now we want to think about, okay, what else can we argue about instead of Booleans, instead of true and false? So there might be package versions. So just what you think about. There may be program variables, so there may be integers, there may be strings, there may be floats, doubles, whatever. You may even have regular expressions. And so what we want to do is we want to integrate all these into these logical formulas. And so what we do is we replace Boolean variables. So we replace our bool A by a Boolean expression that can be X is between these two package versions, or that can be just an expression over numerical variables, whatever numeric means here. You cannot really see. You also need to specify what the type of X and Y is, like in program. You might even mix weird stuff, like you might have addition over floating point numbers, and then you might have a bitwise OR. Or you do string operations, all the stuff. And then you get to formulas that look much more complex, and they are, but structurally they are still the same. So you have this existential quantifier, how it's called in logic, which means is there an assignment to a variable? In this case, this would be a 64-bit integer, this would be a double, and then there is more than just logical operations, of course, because, well, we have more complex data types, so the operations are more complex. But structurally, it still looks the same. And this would be what we call SMT, Satisfiability Modulo Theories, so it's still a satisfiability question, but about theories. And theories would be these essentially the data types. So it would be the theory of package version, the theory of integers, the theory of floating point numbers, and so on. So in a nutshell, I always claim I explain how SMT solvers work in a minute, and I always take 3 or 4 minutes, but anyway. So in a very simplified scenario, an SMT solver combines a SAT solver, which solves only this Boolean construction, and you combine it with theory solvers. And the theory solver, you have multiple of these usually. One theory solver deals with one theory, so you have one solver for strings, one solver for integers, and so on. And the idea is that this one deals with a Boolean construct, with your ands and ors and negation and all the stuff. And this one, the theory solvers, only deal with a list of constraints. So you have no combinatorial problem from the logical side there, but really just a set of relations or a set of inequalities, something like that. And you have a formula as input. Then the SAT solver gives you an assignment to the Boolean structure and totally ignores what happens inside these theory expressions. And the theory solver then checks whether it works. So assume we have x, which now is an integer variable, let's say, and we have a bunch of constraints. So we say x needs to be greater than 0 and x squared should be larger than 0 or x smaller than 0. And then x cubed smaller than 0 or x equal to 3. And then your SAT solver would come around and say, oh, let's assume these two are true. That's a good start to making the formula true. And then the theory solver would say, great, that works. That's what we call SAT. And it also tells us, oh, and by the way, x assigned to 1, that works. And the SAT solver continues because it hasn't satisfied the third part yet, and it says x cubed smaller than 0. I hope that most of you, when they look at these for 2 seconds, see this is probably not good, because if x greater than 0, x cubed cannot be smaller than 0. But the SAT solver totally ignored that. It only looks at the Boolean structure. And then the theory solver will say, yeah, no. That doesn't work. It's unsat, unsatisfiable. And it also gives us a reason why that is. And that's exactly what we call a conflict. And then the SAT solver learns from that. It adds it to its formula, comes again, tries a different combination. This time it works. And this goes in cycles until both of them are happy. Then it's SAT. Or until the SAT solver essentially runs out of ideas how to do it. And of course, it doesn't run out of ideas. It's provably exhausted all possibilities. But yeah, think about it tried everything. But in this case, it works out, and it figures out, okay, x should be 3. And if we look now, okay, x is greater than 0, x squared is greater than 0. This one doesn't need to be satisfied because it's Boolean OR. X is 3, so we can ignore that one. And this is a negation, so x cubed is not smaller than 0. So it works out, we have a solution. And this is essentially how an SMT solver works. There are all kinds of details. So for example, if you have multiple theory solvers, there's a lot of complications there. There is a bunch of very clever people that fine-tune all the details, but let's stop there for now. Then I claimed we are solving hard problems. And if you have never heard of algorithmic complexity, then ignore the slide probably, but I assume you have probably heard something of like n squared, exponential time, something like that. If you actually know what all that means in details, a warning, what I'm telling you now is extremely simplified and borderline incorrect. But it gives you a rough idea. So, the SAT part is already NP complete. It's one of the NP complete problems. So already the first part in this diagram is already pretty hard. And then these shorthands are all the theories, or the most important theories in the community. So UF is the most easy one, and congruence closure is essentially a union find data structure. So this is pretty easy. But still some overhead. Then you can have arrays that try to mimic. Arrays are kind of your STD vector. The arrays is kind of a misnomer, but anyway, it has some additional overhead. Bit vectors are pretty much your native integer data types. That's what we call bit vectors because, well, it's a fixed size vector of bits. And if you only do bitwise operations, it's all nice and easy. But if you start to do additions and multiplications, your formula grows. Because what you usually do is you encode it into Boolean logic, and that means you're putting full adders into the SAT solver. And I don't know if you have ever seen the diagram of a full adder for a 64-bit integer. It looks pretty bad. And a multiplier for a 64-bit adder is for a 64-bit integer is horrific. So that can get pretty bad. And well, the formula typically, if you do arithmetic, grows quadratic in size, and that increases your n. So you're already at 2 to the n squared. If you do floating point, you do the same, But for bit vectors, let's be honest, when do you ever use the most significant bits of your integer? You don't. For floating points, you do all the time. You have no non-significant bits. And that means that all the shortcuts you can do for bit vectors, because you kind of can argue about the range, that your integers will be small, it just doesn't work. And that means that in theory, it's essentially the same complexity. In practice, it's much, much worse. And then we're going for arithmetic. So for linear real arithmetic, we use simplex, which is also exponential, worst case. If we have an integer problem, that's somewhat surprising for most people. It actually gets worse in theory. In practice, it's often simpler, but it's really, you never know. If you go for nonlinear arithmetic, then suddenly you have to deal with computer algebra problems, and you actually have like a 2 to the 2 to the n. If you hit the worst case, then yeah, don't hit the worst case. It's and if you go to nonlinear integers, it's immediately undecidable. If you know what that means, it's good. If you don't, it doesn't really matter because we solve it anyway. But there's no guarantee that we can do it. So it can happen that there's no point in waiting because we cannot do it. And then there are stuff like strings, and for strings it's extremely sensitive for which operators you use, but usually it's immediately unsatisfiable. And now that all sounds really bad. And I mean, I've done that for like 8 years now, and on paper all this is horrible, but surprisingly the performance in practice is pretty good. And the point is that for all of these methods that are used, the worst case is really bad, but in reality it's really good. So for example, like the prime example that maybe a lot of people know is simplex. Yes, simplex is worst case in practice, in theory, and you can construct the worst case examples, but it's just incredibly fast in practice. The same is true for SAT solvers, and the same is true for a lot of these methods. So the context here is formal verification. I mentioned that before, and formal verification is very different than a lot of other areas. So from someone that does formal verification, you will usually not have statistical stuff like in 90% it will work, or you will not hear it's probably correct, or well, we haven't found any error, or stuff like that. Or what's very nice, if you talk to people that do linear optimization, you will often get that, yeah, what we give you is very close to an actual solution, which is, yeah, but I want an actual solution. Or it works, except if you do this really stupid stuff. No. If the solver says SAT, it's SAT. And the model you get, the assignment, it is a solution to your formula. If it's unsat, there is no solution. And it can do unknown or undecidable logics stuff. But if these are not satisfied, go file a bug with the solver, and it will be one of the high priority bugs. So there is I will tell you in a minute about a competition between SMT solvers. If your SMT solver has one incorrect result, it's essentially equivalent to a disqualification for the whole solver. So this is a real thing. And this is the most important thing to understand about formal verification. So, of course, the pure question of satisfiability is not really that interesting in many cases, and so we do a lot more. We've already talked about the variable assignment, so the solution itself. But you can also, if it says there is no solution, you may ask, why is that? Then you get unsat cores, gives you some insight there. You might want to have more than just this is a solution, but you want to add quantifiers in the mix. One special case about that would be optimization queries. Not just give me some solution, but give me the best solution according to some objective function. And then, yeah, they're interpolant. So if you have like two statements and you want to have a statement that is kind of in between logically with special properties, if you're really, really interested in provability, since few years, some of the solvers can actually give you formal proofs that you can put in your favorite interactive theorem prover, like Isabelle, Lean. And what some can even do is like synthesize formulas. Like give you a large specification kind of, and it will try to construct a very precise and concise, very short characterization of what you're asking for as a formula. And that can even mean that it generates program code in an abstract way for you. So this is the goal. So there's a whole ecosystem here, and that's probably for people that will actually want to use it, the most interesting. There's a bunch of solvers. So these are the 3 most well-known. CVC5 is a university project by Stanford and Iowa. Yikes is from SRI, which is a research institute in the US. Z3 is from Microsoft Research. But there are a bunch more. I think all of these are still supported. Most of them are, at least. But most of them are research project, and if the professor retires or whatever, sometimes these become unsupported. Almost all of them are open source projects. So if you have an application and it doesn't perform well for you, go to the issue tracker, file an issue, and say, hey, Nikolai, which is the main developer of these 3, here's an example, and your solver is really bad. And Nikolai tends to take this personally. So if these 3 is bad on an example that should be easy, you have a good chance that he'll fix it. I already mentioned there's a yearly competition. So there's an easy way to figure out for your type of application. So that means which kind of theories you use, which solvers are promising to use. And all this is kind of backed by the SMTlib initiative. It collects benchmarks. So there is like 200K benchmarks, which from a lot of logic. So logic would be combinations of theories. And if you have an application for that and solvers are maybe not that well performing and you want that long-term solvers become better, submit benchmarks. Because once you get your benchmarks in, which is just a matter of add some metadata in a predefined format, stuff like that, then the solvers have to compete on your benchmarks in the next SNT comp, which is kind of the main performance indicators for solvers. And then solvers will become better on your benchmarks. There's a standard input language. So if you want to use them, there's a well-defined input language. There's a standard for that, and all the solvers support it. Write the input once, run all the solvers. There are some, as usual, open source projects. There are some exceptions, but generally that's true. And there's also quite a bit of tooling, like syntax highlighting, a standard parser. There's a debugger that you can use, all this stuff. So from what I've seen, it's one of the more open communities in terms of interacting with them, getting to know which solvers there are, how to use them, and so on. Okay, and what we'll do now is I'll do a few case studies, what I found interesting and a bit diverse projects to maybe see what you can do with them, because usually if people say, oh, we're using SMT solving, or if the solver developers try to sell it to you, most of them will tell you, oh, we are verifying program code. That's like the go-to application. And to a certain degree, that's true. And I will also show you some program verifications. But there are much more interesting and easier things that you can do with it. Or no, easier in the sense of more normal people have these problems, because program verification is a pretty difficult thing to do. So let's start with standard one. I already mentioned CBMC. It's been around it's been around for a long time, and yeah, you can see I checked Google Scholar. There are almost 4,000 publications that kind of work on or with CBMC. And what you do is, like the easiest case, you give it C or C++ code, and it will give you stuff that fails. And it can also tell you, well, it won't segfault, at least not in this kind of way. Truth be told, in my impression is that a lot of stuff that it tells you will nowadays be caught by a VM warning. So, but it can still do interesting stuff, but then you have to look a bit deeper into it. And I've never worked personally with it. So, something completely different. You have maybe heard of RoboCup, which is an international robotics competition. And one particular program we had was with the logistics division. And the idea here is that you have these round things are the robots. And these are what they call stations. And the task is that one team, so there are two teams here, and one team has, I think, 3 robots, and you have a list of products you should assemble, and each product gets, you get a specific amount of point. And so what you have to do first is say, I want to build this product, and then you have to get your robots to visit the different stations. There's a station to get the base cap, and a cap is always such a ring of stuff, so it's meant to model a production scenario. And then there are what they call mount cap, there are other caps, whatever. So you have a base cap, and then you put other caps in different colors onto it, and the more colors, the more points you get in the end, but well, it must be the product that was requested. And then in the end, there's a top that you need to assemble, and then you have to deliver it. And it combines all the stuff of planning what do you want to do, what is realistic in this time frame, actually figuring out which robot should do which subtask, all the stuff. And it has been around for quite a bit, and traditionally people have been using specific planning tools that use like a rule-based approach. And it turns out that if you encode it in a reasonably efficient way, like for SMT, it's always a question, how exactly do you encode it? And throw it in SMT solver, it's competitive with what they've been doing for years. So it's really essentially just doing it with all this planning approach with an SMT solver is competitive with the current state of the art of research. Then I already mentioned the LLVM optimizations. So you probably want your compiler to not mess with your code when it optimizes it. And assume you have this line of code, which is kind of weird, but assume there are like some macros there, or it already did some constant propagation, whatever. And then I would argue, well, it's the same, right? But if you look into it and know your IEEE standards, you know there's this thing called minus 0.0. And if you put that in, then y is suddenly no longer plus 0.0, but minus 0.0. And there you might argue, well, it's still 0. But if you take 1 over y after that, for whatever reason, then it might not just segfault because it's a floating point error because you divide by 0, but if you have these exact values, you might end up with plus infinity and minus infinity. And this makes a difference. And so what they did is they added a workflow where if the user implemented an optimization path, then there's an existing tool alive that encodes this into the SMT solver and checks that the previous code and the code after optimization for every possible instantiation of the optimization is correct. And they extended it with what they call live jacket, which is essentially adding floating point support to the thing. And they used it, and great thing, they verified 43 passes, but there are also like 8 passes in current LLVM. Probably by now most of them are fixed, but when they did it, 8 passes were just incorrect for certain cases. And well, probably it was correct for most of your inputs. But that's a nice thing about formal verification. It also catches all the edge cases. And yeah, they actually caught a lot of, well, a lot. Depends on what you consider a lot of bugs, but 8 bugs in LLVM is probably pretty nice to have fixed. Then we had a project where we dealt with automatic configuration of cloud applications. So assume you have a big website where you cannot get away with just taking a big virtual machine, but you have to like deploy multiple databases as a backend, multiple web servers, a load balancer in front. And then you have the question, okay, which virtual machines do I need? Which is still cost effective. I mean, you can always just buy the very large virtual machines, but it's probably wasting money. But you also have to figure out, okay, how many database backends do I actually need to serve so many requests in the front end? And so what we're doing here is we specify these in a formal way where we say, for example, oh, there is our MySQL server. It needs 1 GB of memory, and it can serve at most 3 WordPress instances running in front. And if we have a WordPress instance, we can say, okay, there should go a reasonable number. It can serve so many queries. It takes 2 GB of memory, and it needs at least 2 database backends for redundancy. And you have a load balancer, and for load balancer to make sense, you need like a lot of cache. So you need 7 GB of memory, and you should have at least 3 WordPress instances behind it, because otherwise it doesn't make sense to have the load balancer in the first place, for example. And then you scrape all the VM specifications from AWS or whatever you want to use. And then the tool does 2 things. So one is it wires the components together. So in this case, it's not that interesting, but if it gets larger, then you at some point have the question, which WordPress instance is connected to which database backend, for example. And then it allocates your components to virtual machines and tells you which virtual machine to buy, and tries to do that in a way, or does it in a way that you pay the least amount of money for your virtual machines. And then you can add all kinds of additional requirements. So for example, you could say, well, both all my databases and all my WordPress instances should not co-located on the same host. Because if you're running multiple databases for redundancy, they should not be on the same host. Yeah, and also here, there are people that are doing that with custom graphs theory stuff to figure it out, or you can just throw it as a SMT solver. It performs roughly the same. And you have the benefit that it's extremely flexible. You can just add in additional constraints, whatever they look like, and it can still do it. And then there's Amazon, and yeah, they do this checking of access policies. So they call it the Alcova. That's their semi-internal project name. And essentially what they do is they check all kinds of security policies against each other. They have some built-in policies where they recognize patterns, how people inadvertently open up their resources to the whole world. So if you forget a negation, and if you've ever used these these policies, there are a few weird things in the specification language that make it very easy to actually negate what you want to say. So instead of saying, I only want these people to have access, you suddenly say, I want to have all people except these people to have access. And then, if I remember correctly, it was for AWS that the order of constraints was important. And then suddenly weird stuff happens. Like, think your old IP tables rules. If you mess up the order, well. And then you can have like base policies for your whole account, and base policy for your bucket, and a policy for folder, and they kind of cross-check all these, and then you can tell it, yeah, I want my specific policies only be more restrictive than my base policy. And then, they do all this automatically. Whenever you change a policy, they do all these checks. And depending on how you use it, it can, for example, say that whenever you make it more permissive, then your manager has to sign it or whatever. So stuff like that. And actually, it seems that since they do that, the number of issues or cases where people suddenly publish S3 buckets has dropped significantly. Of course, you can still do it. They allow you to do it. But more often than not, you would not want to do it. Another regular issue there apparently is if you have multiple companies that kind of share resources, and then also weird stuff happens. And they use it extremely extensively. So the 1 billion SMT queries a day, they mean that very literally. So they have very nice statistics about that, and they are very eager to make SMT solvers faster because they pay a lot of computation time on that. They also have other stuff. They also do regular program verification on their how's it called, identity management systems. And finally, a quick promotion for my employer. So there are also very special programs you might want to verify. And what we do is we verify smart contracts. So what that means is we take EVM bytecode. So EVM is the Ethereum virtual machine. So it's essentially just another bytecode for what I'm concerned. And you have a specification, which is essentially unit tests on steroids. So what that means is you write unit tests, but for certain variables, you don't specify a value. So you call a variable, you call a function in your unit test not on some specific input, but you tell it, it's use whatever input, and please show me that it works for all inputs. And then, we have our intermediate language. Think of LLVM intermediate representation, but very different, but the idea is the same. We do a bit of static analysis, and in the end, we call an SMT solver. And then we can show that, at least for the properties they specify, there is no way to violate it. And that can, for example, be you cannot just take money out of the smart contract, or you cannot, I don't know. So depending on how much you know about this DeFi ecosystem, you cannot front run another one and gain money from it. You cannot, a very typical bug that people keep doing all over again, if you do a transaction and you send money to yourself, and so the sender and the receiver of the money is the same ID, then there is a common bug that you first decrease you calculate what should be the new amount for the sender, what should be the new amount for the receiver, then you write both in, and suddenly you have more money, because the value you calculated beforehand is your old value plus the amount of money that was sent. But the information that you also spent money in the process is kind of lost. And we just had a bug with a customer that did this bug again, and it cost him like $5 million US dollar in a fun currency, whatever. It's a nice thing about smart contracts. So if you hear people talk about software verification, they will usually tell you, oh, it's a great idea, but it doesn't scale. And that's kind of true. So the problem with actual programs in reality is that you have like hundreds of thousands of lines of code. The nice thing with smart contracts is that you pay money to execute them, and you don't pay like CPU time as you do on the cloud, but you pay like much more money per instruction. And so people have a strong incentive to have small programs. And so the whole scalability issue here is, not that bad, and you can kind of concentrate on the interesting questions. Yeah. So I think that's what I wanted to present, and I'll be happy to take any question about anything I talked about. All things you always wanted to ask about SMT solvers. And of course you can also talk to me afterwards. Thanks for your attention. So the question was how the approach will be integrated in like a corporate development and compared to fuzzing. Yeah, so let's start with the second because this is much easier or quicker. So fuzzing is, you call it on more or less random inputs, and fuzzing is really good in a lot of cases to find bugs, but it cannot prove or show that there is no bug. You can never have a confident statement about that, and this is what you can do here. So about like a enterprise environment, I guess it goes into that you have large code bases and the scalability. So there are some approaches. So Microsoft has done some interesting things where they do modular verification, so that they kind of automatically infer specifications for your functions, so that you have a logical boundary at your function call, and they semi-automatically say what should hold, and it's kind of a back and forth, and sometimes it works nicely, but in general this automatic inference of stuff and what stuff exactly is almost doesn't matter, is an undecidable problem, and it's one of these that is very hard to do. So that's yeah. So in this sense, I'm really not sure. Where it helps is all these little tasks. So for example, there have been projects where people verify that your refactoring mechanisms in your IDE are actually sound. That can help. Or there have actually been all these little toolings, or you just verify your base library, or you just focus on a specific function where you know this is super critical, there's no bug, like your crypto library, then maybe I know that from a security perspective that's not right, but if your crypto library is proven to be safe, then maybe it's not that bad if the rest of your code is a bit fishy. Of course, if you're doing protocols on top of that, this doesn't hold. But you can at least start with your basic stuff. And otherwise, I mean, what Amazon is essentially doing, they are paying domain experts to manually do this modularization. So they will manually write formulas for specific functions, and then instead of proving your whole code base, they just prove this function behaves that way, and then this kind of is a shorthand. Instead of calling this function, the solver will just put in the formula there. And truth be told, this is also what we do for smart contracts in certain cases. But yeah. Any other questions?
Yeah, so in the case of figuring out whether the firewall rules are wrong or whether the smart contract is buggy, it feels like it's really difficult for me to imagine what kind of a constraint there is. It sounds like you're basically telling the constraint solver to please tell me if this does what I mean it does. And this is kind of hard to understand for me.
Yeah, so the question is, how do the constraints look, for example, for firewalls or stuff? Like how do I specify what do I mean, what do I want it to say? And yeah, this is a problem. And in many cases, this is like you have the scalability issue, and apart from that, this is the most difficult thing. And the problem is, make it for the regular user easy enough to say what you actually want to say without requiring that the user knows what the tool is doing in the backend. And this is difficult. There's progress on that front. In a lot of cases, you have like, you hire some people that kind of know both worlds, and you have a like domain-specific language that has constructs for the most common constraints. So, for example, for a firewall, I would imagine that you could have a tool where you could say, yeah, there is a, I don't know. You would probably have some. So what you often do is that you have kind of specific theory that you build yourself as a preprocessing that argues about, okay, is there a way to hijack a connection, and that has some shorthands for that, and then how exactly to model that is someone does it for you in a very clever way, but yeah. That's, on the other hand, I mean, if we're talking about fuzzing and we're not talking just about does it segfault, it has the same problem, right? I mean, what is an error? How do you specify what the error is? And if you can formally specify this as an error condition, then it's essentially what the SMT solver works with as well. But yeah, so for us, a lot of time goes into telling people that use our tool how to write specifications. Okay. Any other questions? Okay, then thanks again. And if you come up with any other questions later or generally interested in SMT solving, feel free to drop me an email. And have fun at FrOSCon.